All right, hello everyone. It's the 19th of February. LeetCode's been dropping the ball these days, which is good because it gave me time to deal with this. I did not see anything more, but I did check this, you see. So it's number theory and math. So we're gonna go through the hints today, see if we can get anything out of it. What is sorted array, distinct integers, and target value, return the index is found. If not, return the index what it should be. It would be if it were insert. And they drop in balls, but we cannot drop balls. We have to keep working, right? Cannot be like, oh, the daily challenge is gonna be easy for this month, and then now we're just gonna slack. No, we cannot do that, right? We cannot do that because maybe we should do bisect left. Yeah, if we go bisect left, yeah, bisect left, I think I can just return it. I think I can just return this. Yeah, bisect right, I have to check. Bisect left, basically. I think I just return this. It should be fine. Yeah. Oh, wow, 2018. That was the last time. Huh. Okay, so that was nothing. That was just, we do this for documentation purpose. To show that we're done for this day, 35. All right, let's see. Let's see what does the hint tell us. First one, let's go in reverse order from target and target to 1, 1. So now we can move from this, and this. Of course, if x is even, and this if y is even. So this way, at least we can reduce the number of possibilities a little bit. We're there a little bit, right? Which means if let's say if y is not even, then we cannot move down. And if x is not even, then we cannot move left. Okay, reverse order, then what? When is it optimal to use the third and fourth operations? When is it optimal? What do you mean, when is it optimal? What is optimal if I don't know when is it optimal? What do you mean when is optimal? I mean, third and fourth is to reduce it by half, so it has to be even, right? And then we can reduce it by half. And if we reduce it, because we want to move to 1, right? So at the end, we have to move down to 2. We have to go down to 2 and then divide it by half, or you divide by 1. You can think about it this way. We just need to get one of them to 1, right? If we get one of them to 1, then we can always go back. Is that true? If we get one of them to 1, then we know from that point I can always add 1 and then divide, add, and divide, add, and divide. Yes, so we need to get one of them to 1. So no matter how, we want to get one of them to 1, okay? So that was the goal. We want to get one of them to 1. It is optimal to use the third or fourth if we get to 2, like power of 2. If it's power of 2, we can do that. That's the optimal to use it. So you're saying we're trying to do the plus, to do all the pluses so that we can reach power of 2, which means given two values, all right, given x and y, we can do any amount, and we can do any amount plus x, right? And then we can plus that, then we can plus, yeah, just any amount of plus. If we can reach power of 2, if anyone become power of 2, then we're good. That's why 4 and 7 is good, because 4 is a power of 2. So now the question is, how can we decide whether it's possible to reach power of 2? I mean, power of 2. What are we saying about power of 2? We start with x and y, right? We can say we can do any number. We can say x plus any number of y, right? And then you have to go one direction and then the other direction. Right? Either plus, keep plussing, and yeah, that's the only way you can go. If you want to go horizontal, you just plus y, plus y, plus y, plus y. And then you want to go vertical, and then it'll be plus x, plus x, plus x, plus x. And then plus y, and then plus x. So you just go zigzag to the right and up, right and up, right and up, right? That's all you do. Zigzag to the right, and you go up. And to the right, and you go up. And every time you to the right, you add a current y. Right, every time you go up, you will say y plus m2 x plus m1y. And then when you go on again, that will be plus m1y plus m3y plus m2x plus m2y. What do you see in this? We're trying to find, any pattern in this. I don't see any pattern, man. If I can do to reach 2 to the k, that would be good. But if I cannot, nah, keep going. Think how GCD of x and y is affected if we apply the first two operations. The GCD. GCD is affected. Is GCD affected when you do plus? Well, GCD. Let's say x is kg. K1 P1g plus Q1. Y is P2g plus Q2. Okay, and then no, just P1g and P2g. This is the common divisor. Right, this is the common divisor. I can just say P and Q. Okay, and then because we times So if we move right, then it will be PG plus M1QG. So it will be P plus M1Q times G. Now we know P and Q are coprime, right? So what do we want? Right? What do we want? We want to after the move, it depends, right? It depends on the number of steps. If the number of steps I take is multiple, right, of P, then, well, actually, if we move once, it'll still be the same. And if we move twice, if we move the same number of times, then it'll become, the GC will become bigger. But what does that have to do with reaching, power of 2? We need to reach power of 2. Maybe we don't need to reach power of 2. This is just how I think about it at the moment. I still don't know. Hit number 4. How can we check if we can reach 1, using the GCD value calculated above? Okay, just depending on how many moves you make, the GCD will change, right? The GCD will change. But eventually, if you want to get down to 1, are you telling me that every time you plus y, every time you plus x, that GCD is still there? Alright? The GCD value is still there. And what happens if you divide? Well, if you divide, the GCD is still there. Right? Are you telling me that the 2 has to be coprime in order to reach? I don't believe this. But if you're thinking about it, the only way to move is to plus the other one. Or plus, right? Every time we plus, the original GCD is part of the new thing, right? The original GCD is part of the new thing. So if the GCD itself, if you add and you add, we always have the GCD as a factor in the new x and y, if you just add. And when you divide, right, if your GCD is not divisible by 2, then when you divide, you will never be able to remove that GCD, right? Let's say if the GCD is 3, which is the case of this. So no matter how you do, right, you do this x plus y or y plus x, no matter how many times you do, 3 is always a factor in the current x and y, right? And at a certain point, you need to divide. And because 3 is a part of it, so no matter how you divide, there will always be a 3 out there. That makes sense, right? There will always be a 3 out there. So you can never divide yourself or plus yourself back to 1. That's not possible. So that's how you do it. So this is not possible because its GCD is not divisible by 2. Now this GCD is 1. How do you think about GCD is 1? Now if GCD is 1, what does that mean? GCD is 1. That means if you keep plus, well, you will have some GCD, but the base is always 1. And then you will divide by 2. That also doesn't really matter. Are you saying that as long as its GCD is 1 or power of 2, if GCD is 1 or power, if the GCD is, let's say not power of 2, anything, it's not power of 2, even if it's divisible by 2, because eventually when you divide, you will hit a odd number. So the only way is for the GCD to be 1 or power of 2. That is crazy. Dude, that's crazy. Seriously. So what, we just check, but why it will always work if GCD is power of 2? Well, if the GCD is power of 2, I can always divide, right? If the two things is power of 2, doesn't matter how many power of 2. Let's say 3 times 2 to the some power, 2 to the 3, all right? And 5 times 2 to the 3. How about that? And then we can do whatever we want, and then we'll divide. So if we divide, after get rid of all of them, we'll end up with, let's say, 3 and 5. Now the question is, can 3 and 5, well, 3 and 5 is actually possible because you can do 3 plus 5, and that's not a good example. 3 and 4, that's not a good example. 3 and 6, no, because 3 is 3 and 7. How about 3 and 7? 3 and 7, okay? If it's 3 and 7, yeah, because as a powers 2, we can get rid of all powers 2 if there is some other GCD out there, then it's not possible because we cannot get rid of that factor. So the only thing now we're thinking about is that two values are co-prime. If they are co-prime, 3 and 7, if it's 3 and 7, can we do it? Well, if 3 and 7, then there's some, I don't know, we can do whatever, right? If it's 3 and 7, then what will happen? Now we want to add. Now we cannot divide, so we have to add. And each time we add, the only way to create new ways to divide is if we add we're going to do 3 plus 7, right? That will be 10, 10, 7. No, let's do 310, 310, get down to 3, 5. And in 3, 5, we can go to 3, 8. And in 3, 8, we can get to 3 and 1. And from 3 and 1, we can do, 3 and 1, basically we can just go back. Because we can, because 3 and 1, we can just plus, right? 4 and 1, and then go back. Okay, that's, how about 3 and 11? 3 and 11. Okay, you add them, will be 14. And you get down to 3 and 7. Wait, how did you do that? So any two value that's co-prime, is that what you're saying? If any two value that's co-prime, we can always get it to power of 2, one way or another. That's crazy. That is crazy, man. 6, 7. How'd you gonna do 6 and 7? Well, 6, 7 is the same as 3 and 7. 9 and 7. 7 and 9. How about 7 and 9? 7 and 9. That's 16. Dude, this is not working. How? Like, why? 11 and 7. 7 and 11. 7, 11. That's 18. Right? 18 plus 7 is 25. 25. 25 plus 7 is 32. Alright, can we do that? 7, 11. 7, 18. 7, 25. 7, 32. Yo, man. Wait, there gotta be a... Is there a... I don't know. Yeah, because the sum of all odd numbers is 2 to the n. Yeah, because if you have any even numbers, I can always reduce them to an odd number, right? And if it's even numbers already, power of 2, and then that's it. We're good already. If none of them are power of 2, if none of them are power of 2, we can... If none of them are power of 2, we can simply say, I don't know, none of them power of 2. Then we take their GCD. If the GCD is not 1 or power of 2. Okay, so but to begin with, we will divide everything by 2. Okay, we'll divide everything by 2. So take out all the 2's. So we have something remaining. So both are odd values. And if we have a 1, then we're good. If we don't have a 1, then we find the GCD. If the GCD is not divisible, if the GCD is not 1, which means if they're not co-prime, and there's no goal because we cannot divide anymore. And no matter how we add, we just cannot divide down. Okay, that's good. So now the GCD is 1. So now what we have is odd numbers, co-prime odd numbers. Okay, so we have 2m plus 1 and 2n plus 1, and they're co-prime. They're co-prime, which means they don't share another thing. Now the question is, how, like, can we get this? Well, what we can do is m or n, right? Whatever it is. An odd value. And an m and an n themselves must be odd. Because if it's even, we have already, we'll keep doing, right? So m and n must be odd as well. Then what? Yeah, we have an odd value. If we plus them together, That's 2m plus n plus 1. Right? And that's divisible by 2. Okay, then we'll have either 2m plus 1 or 2n plus 1. We can go either one, which doesn't really matter, right? It doesn't really matter. And if we would go so we have this and this. Then if we go, it's going to be the sum of these two. What do we want? We want it to be power of 2. Yeah, how about 911? I have 20. And then go 9 and go 11. Then I have 29, 9. Oh. I have no idea how to proceed. Hold a second. You know what? Let me try 9/11, right? This is what we. Let's say true. I actually don't know. 9/11. It is true. How? So are you telling me that what we just analyzed is correct? But I don't know how. How can you go from 9/11 to 1/1? Oh, in other words, how do you find 2 to the something power from 9 and 11? Just keep adding. I don't know, man. I think I know how to do it, but I don't know the proof. I do not know the proof. How do I prove that given 2 odd values that are co-prime, we can always get back down to 1 and 1? I don't know. I know for odd values we have this property. If you add all of them together, it's going to be 2 to the going to be power of 2. But it has to start adding from 1. I mean, I can try, write it out first, but what's the proof, man? What is the proof? Without proof, this is just solving the problem, not really make it work. That'll be something like this. Okay. What I know so far, if target X and target Y has GCD not equal 1, right? As GCD not equal to 1 or power of 2, it is no matter how we add them, right? So first of all, following the hint, go from target x and target y back to 1, 1. This requires us to do x plus y to make the following moves. Right, when we make the following moves, what we have is x plus y, y, x plus y, x divided by 2y, and x, y divided by 2. If that has GCD not equals, no matter how we add them, the new x and y will always have a factor, right? Factor not divisible by 2. This means we can never reach 1 by division. Thus, right, we can first take all factors of 2 away from target x and target y, and then check the remaining x, y GCD. If it is not 1, then it is not possible. However, what I currently cannot prove is that if x and y are co-prime and odd, they can always go back to 1 on 1. I can convert this problem to proving we can always generate, right, create power of 2 by some scheme of addition, by some movement of x plus y, y, and x plus y. But I do not know how. I do not know how to prove this. Maybe we can try. See if it works. It works, but again, I don't know how to prove. How do we prove that? Yep. It works, but how do we prove it? How do we prove it? What does that mean? Okay, we say it's multiply of multiple of 2. Right? It's a multiple of 2. Then what? I can divide by 2. So it's x times something. It's inner plus 1. If it's divisible by 2, we can keep divide. What are you trying to do? I don't know. What's the proof? Okay, this is the key. GCD is power of 2. So necessary yeah, this is correct. I get on to it has to be 1. If x is even, yeah, we can get to the situation the both odd. So we get them down to both are odd. If both are odd and x is smaller than y, we can go x plus y. So x plus y become even. So we get a smaller pair of odd. if x is larger than y, so we can continue to go smaller, smaller until both odd, and this is equal to this. Wait, what the hell is this magic? So instead of thinking of a power of 2, we have 2 odd values. And the goal is to make them smaller. Because 1, 1 is both are odd. So I can always add to become an even. And I'll divide. That'll definitely be smaller than the previous. Odd plus odd is even, and I divide by 2. And I can keep adding and divide, keep adding and divide. So eventually, because you keep going down, then go down to 1 on 1. Lower bit. Yeah, that's a good way. Oh. So the key idea is this. I did this one already, but I got stuck here. It's not to find they are power of 2, but to say that we can always bring it down. If both are 3 and 3. Then the GCD is not 1. The GCD is the thing. Right? 3 and 3 is impossible case. Actually, I'm not quite sure. That's 3, right? Yeah, that's 3. Oh, that's the proof. Man, what do you think? What I think is good. The full proof is here, is by Lee 215. How do you oh man. Okay, that I should say. So I was close. I realized that we can get down to two odd numbers for x and y that are also co-prime. Well, then I was trying to see if we can use some sort of mechanism to add x and y to reach power of 2. But the correct method is to decrease them and see if we can reach 1. Now, since x and y are both odd, we can always do x plus y divided by 2 to bring the value, to bring the larger of x and y down. Now, if this new value is even, we keep dividing it by 2. Then we will reach a new pair of odd x and y. Repeat this process, and eventually, eventually we will reach a point, we'll reach a point where x equals y equals 1. Well, reach a point where x or y becomes 1. Yeah, because you divide, you divide, you keep dividing, and you divide. Eventually we'll reach a point where it becomes 1. And we know that once 1 of x or y becomes 1, we can return back to 1, 1. Or we can keep doing the trick of x plus y divided by 2, and eventually we will have both x and y reaching 1. Thus, from this analysis, we can even simplify the check to seeing whether the GCD of target x and target y is power of 2. LeetCode 215 uses this check, x and minus x, right? X and minus x. Actually, let me see. X 4 and minus 4 is 4. Oh, I don't think you can check in Python though. How do you check in Python? Python, the negative is bit count. Oh, you can check. Because 4. Minus. I know Python does minus very differently. Wait, hold on. Yeah, we have to put a minus value in here. That's not right. Hold on. 4 is 1, 0, 0, 0. Minus will be 2's complement, right? So a complement plus 1. Oh yeah, it should be equal. If it's not, then it's 2's complement. Yeah, g equals math.gcd, target x, target y, return g equal to g, and minus g. All right. That's a very good problem. Yeah. No, I cannot count this as I done, and I did not do this.